Hello. Today, in this video, I'd like to talk to you about buffers. First, we're going to ask ourselves the question, what is a buffer? We're then going to go ahead and figure out how to calculate the pH of a buffer solution. And then finally, we're going to think about what happens when you add acid and base to a buffer and how you can make calculations with pH there. First, though, what is a buffer? Well, a buffer is a solution that resists changes in pH when acid or base is added. To show you an example, I have here two solutions, one that is distilled water and another that's a buffer solution made of acetic acid and sodium acetate. And you'll notice if I add to my distilled water here a small amount of 0.1 molar sodium hydroxide, so really not that concentrated of a base, we're going to see if the pH of this changes. Now, in order to see that the pH of my distilled water changes, I'd add one other thing, and that's an indicator. I've added phenolphthalein to my distilled water, and so if I add just 0.1 molar sodium hydroxide to my beaker of distilled water with a bit of phenolphthalein, let's just add 1 or 2 drops here. 1, 2. You will already notice I'm getting a nice pink change of color. So this solution is not a good buffer because, seeing from our indicator change, that solution rapidly changed its pH when I added the 0.1 molar sodium hydroxide to the solution. The pH shot up and became very basic. Now, here I have my buffer solution. You'll notice, let's go ahead and add the same amount of 0.01 molar sodium hydroxide to this. And again, I had the phenolphthalein in here. So 2 drops, and you'll notice this solution does not change its pH. In fact, I could add a lot more of my base, and I still don't get a change in the pH of my buffer solution because it's able to resist this. Now, why buffers works is because they consist of either, number 1, a weak acid and a salt of its conjugate base, or vice versa, it's going to consist of a weak base and a salt of its conjugate acid. Now, why this works, let's take a look at the example that we have here with our sodium acetate. And so in that solution that was a buffer for us, I had put just a small amount of acetic acid, C2H3O2, and the salt, sodium acetate, NaC2H3O2. And you'll notice that acetate, C2H3O2 minus, is the conjugate base of my acid, acetic acid. And so when you put these in solution, they create an equilibrium reaction. C2H3O2 is in equilibrium between H plus and C2H3O2 minus. Now, when I go ahead and add then some acid or some base, those are going to react with either side of this equilibrium. If I add base, that's going to react with the acid side of the equilibrium. It's going to shift it, but that shifting is going to go ahead and mediate exactly how much that pH changes. Because this is an equilibrium reaction, this buffer can absorb some of that acid or base without really changing this H plus concentration very much. And we know that H plus concentration, that's related to our pH. And so that's how our buffers are going to work here. Now, this can consist of any weak acid and salt, or any weak base in the salt, but what it cannot consist of, cannot consist of a strong acid or base. If we have a strong acid or a strong base, that doesn't exist in an equilibrium reaction, and it's this equilibrium shifting that allows my buffer to work. Let's go ahead and take a look at an example then of how you might calculate the pH of one of these solutions. So here our question reads, what is the pH of a buffer made by mixing 50 mils of 0.24 molar lactic acid and 50 mils of 0.2 molar sodium lactate. So the first thing we want to talk about is, well, what is lactate and what is sodium lactate? What's lactic acid? So lactic acid is HC3H5O3, and then sodium lactate, therefore, must be Na with C3H5O3. So it's got the anion part there. And that's going to form a reaction. We can go ahead and write this as a hydrolysis. So we have our lactic acid plus water is in equilibrium with H3O plus, and our sodium lactate. I'm not going to write the sodium, I'm just going to write C3H5O3 minus. Now, to calculate this pH, because it's a weak acid, weak base equilibrium, we're going to go ahead and use an ice table. Now, it would be great if it was easy, and I could just plop in my initial concentrations from here. But notice I mix these two solutions together. And when you mix two solutions together, you create a dilution. And so we need to account for both of these solutions becoming diluted by the other one. And so what we're going to do is we're going to use our dilution equation, M1V1 equals M2V2, to find the new molarity of each solution. So to do that over here, I'm going to do it for the lactic acid first. M1V1 equals M2V2. Going to go ahead and plug in my 0.24 molar times the volume 1, which is 0.05 liters, equals molarity 2, which I don't know, times my new volume, which is 50 plus 50, or 0.1 liters. When I plug that into my calculator, it looks like the molarity I get for my new lactic acid, M2, is going to be 0.12 molar. So you notice it went down by a factor of a half. And in fact, this one would go down by a factor of a half as well. And so calculate it out if you have time, but we're going to find that it's 0.10 molar. So then I plug my numbers into my equation here. 0.12 molar for my lactic acid. I've got water not playing a role in my equilibrium. H3O plus is going to start off at 0, and then I have 0.20 molar as my sodium lactate, or my lactate ion in solution. From there, we know that this equilibrium is going to shift. We know that we have 0 H3O plus, it's got to shift to the right. So minus x plus x and plus x. And then finally, I'm going to get 0.12 minus x, x, and 0.20 plus x. Now, taking a look at the Ka of lactic acid, I know that the Ka is pretty small, especially when compared to the molarities of both my lactate and my sodium and my lactic acid. Therefore, we can make the small x approximation that is going to be a negligible change in x for both of those solutions. And so that makes our Ka expression a lot nicer. When I solve for the Ka, that's 1.4 times 10 to the minus 4th equals x times 0.10, or sorry, 0.10. We'll fix that up here and fix that down here, divided by 0.12. When I solve that out, x is going to be 1.7 times 10 to the minus 4th molar. Now that's my H plus ion concentration. So to find my pH, I just take the minus log of that number, 1.7 times 10 to the minus 4th, and I get a pH of 3.8. So you notice this is just like the weak acid, weak base calculations we've seen before, but now we have both a weak base and a weak acid in our equation here. Now, fortunately, there's an easy equation that we can use to calculate the pH of a buffer solution, knowing that it's going to be acid and base. Now, there's a few assumptions that we're making when we use this buffer equation. Now, this buffer equation, also called the Henderson-Hasselbalch equation, we need to assume that the x over here is negligible. The concentration of my weak acid and my weak base is greater than the Ka. If it is not, then we cannot use this equation. This equation assumes that we can do that. But if we use this equation, the way to find it is that if we took our Ka expression for our weak acid, which is just that H plus times A minus divided by HA, that's our standard equilibrium expression for a weak acid, if I took the negative log of both sides, I'd get negative log of the Ka equals, now I get a big mess there, negative log of H plus times A minus divided by HA. Now, I'm mostly concerned about the negative log of the H plus because that's my pH in solution. So let's go ahead and see if we can just solve for that. Negative log of the Ka is negative log of H plus my negative log of A minus over HA. Now from here, we can put in a few definitions and then go ahead and rearrange this a bit better. Negative log of H plus, I know that's just the pH. I'm going to move that over to this side to make it positive. So I get pH over there. From there, I have negative log of the Ka. And so we're going to define that as a new thing called the pKa. That's just the negative log of my Ka value. And then finally, all of this moving has now made that positive. I get plus the log of the concentration of my conjugate base divided by the concentration of my acid. And this equation right here, we're going to call our buffer equation or our Henderson-Hasselbalch equation. It's very useful for calculating the pH of a buffer solution given the concentration of base and the concentration of acid. Now, lastly, let's see what happens when we add an acid or a base to our equilibrium expression. So we have here a buffer is prepared by adding 2.1 grams of sodium fluoride to 50 mils of 1 molar HF, Ka being 6.6 times 10 to the minus 4th. First off, what is the pH? And then, what is the new pH after adding 10 mils of 1 molar HNO3 to the solution? Well, to first find our pH of our buffer, let's go ahead and try to use our new Henderson-Hasselbalch equation. So pH equals pKa plus the log of the concentration of base divided by the concentration of our acid. Now, to go ahead and solve this out, I'm going to first need to figure out the concentration of the base that I have here. Since I already know the concentration of my acid, that's 1 molar. So to find the concentration of my base is going to be F minus, the conjugate base of HF. So to calculate that amount, I know the amount of grams, 2.1 grams, and that's going to be dissolved in 50 milliliters. So I first need to take my 2.1 grams and convert that to moles. And so when I do that, it looks like I get 42 grams per mole for my hydrogen fluoride. And then finally, that's going to give me 0.050 moles of F minus. I'm placing that in 50 mils, so 0.050 moles in 0.050 liters. That's going to give me a nice round concentration of 1 molar. And so you notice the concentration of my acid and my base here are the same. They do not have to be. Buffers can be made with different concentrations of base and acid, but here they happen to be the same. From there, I'd go ahead and plug into my equation. pH equals the pKa, which is just minus the log of 6.6 times 10 to the minus 4th, plus the log, remember that p means minus log here, of 1.0 divided by 1.0. And if you remember from math class, the log of 1 divided by 1 is log of 1, and the log of 1 is just 0. And so here my pH is going to be equal to my pKa. So when I take the negative log of my 6.6 times 10 to the minus 4th, it looks like I get 3.18 as the original pH of my buffer solution. Now that's just the original pH. Now we're going to find out the new pH after we add some acid to this buffer, and this is the magic of what buffers do. When we normally would add a bunch of acid to a piece of water, 10 mils of 1 molar HNO3, that's going to really shift the pH of that water. But because we have a buffer solution, it's not going to do quite as much. Now, the way that we're going to calculate this out is first, we need to react the HNO3 with the base in my solution. And so my HNO3 is going to react with the base, which is F minus, and it's going to form in a completion reaction because this is an acid plus a base neutralizing. That's going to form HF, donating a proton there, and NO3 minus. And we're not going to worry so much about the NO3 minus, but for completion, we want to see that that's going to happen there. And so what's going to happen here? I have HNO3, 10 mils of 1 molar. So 10 mils of 1 molar HNO3 is 0.010 moles. Now, I started off with 0.05 moles of my F minus, and for the HF, I have 50 mils of a 1 molar solution of that. That's also, fortunately, 0.05 moles. Now, looking at the stoichiometry, this is going to be my limiting reagent because there's less numbers, less amount of my HNO3 than there is anything else. And so that's going to go to completion. I'm going to lose all of that acid, and its final amount of moles will be 0. I'm then going to also lose 0.01 moles of my F minus, but I'm going to gain 0.01 moles of my HF. We're not going to consider the NO3 minus because it's not an acid or a base, being the conjugate of a strong acid. So here I get 0.04 moles of my F minus and 0.06 moles of my HF. Finally here, I need to calculate the new concentrations of both my acid and my base here. So the one thing I've got to be careful of is that I started with 50 mils of solution, but I added 10 mils here. So my new volume is going to be 0.06 liters. And so when I calculate my new molarities, I've got to divide each of these numbers by 0.06 liters. And I end up getting here, it looks like a concentration of 0.67 molar. And here I get a concentration of, again, just 1 molar. So from here I can finally plug in to my Henderson-Hasselbalch equation again, the pH of my solution here. I'm going to just extend the page a bit. pH, it's going to be the pKa, which we know is 3.18, plus the log of my base concentration, 0.67, divided by my acid concentration, which is 1. When I plug that in my calculator, I get a pH of 3.0. Lastly, we can just check and make sure that this makes sense. I added an acid to my buffer. It makes sense that my pH decreased from 3.18 down to 3.0 because adding an acid should lower your pH. What the buffer did is make it not lower so much because that buffer was able to absorb some of that H plus and not leave it in solution. Okay, that's been an introduction to buffers. Thank you all for watching. See you next time.